Let me take a very simple example and let us calculate the noise in DSB-SC system, I mean signal to noise ratio. Okay, so let us say you have message m of t and which has uniform power spectral density. So this is the assumption that we are getting now. Power spectral density is uniform. Okay, and as we said earlier, that message is modeled as a random waveform. So the random waveform is defined in terms of power spectral density function in the frequency domain. And let us say it has uniform power spectral density function over its bandwidth, which is assumed to be 4 kilohertz. Right? So uniform power spectral density, so this uniform distribution 0 to 4 kilohertz, this is frequency and this is minus 4 kilohertz. That is, power spectral density function is flat, extending from minus 4 to plus 4. That's what it means. Now let us consider a DSB-SC system, double sideband suppressed carrier system, with the carrier frequency Fc is equal to 500 kilohertz. Okay, and let us say noise is not white but colored noise. Okay, in the derivation part, while we discussing the double sideband suppressed carrier single sideband modulation, we considered white Gaussian noise, but in this problem let us not consider white Gaussian noise, but it is a colored noise. Colored noise means the spectral density is not flat. Okay, let us say the colored noise is given by Sn suffix of is given by 1 divided by omega square plus a squared. So if you try to plot this the density function, it goes like this. Generally white noise means it will be like this, but this one will be like that. So we are assuming that the noise is noise power spectral density function to be something like this. Okay, so in case if you pass this white noise to a filter, some type of filter, then you will get a colored noise. This is white noise, and this one is an example of colored noise. It is not constant, so some kind of a filtered noise. Doesn't matter, just for the sake of argument we are considering this. So in this thing, let us take this constant value a is equal to 10 power 6 pi. Okay, and this numerical value makes sense because if your carrier frequency Fc is 500 kilohertz, the noise power in that bandwidth going to play a role. Okay, and one more data we need, that is signal power, right? So the final data needed is the useful signal power at the receiver, let's say, which is equal to 1 microwatt. Useful power is equal to 1 times 10 to the power of minus 6 watts. Now our objective is to determine the output SNR. So message bandwidth is given, it is uniform power spectral density, and noise is given, carrier frequency is given. That's all. Now let us do the calculation. So you are transmitting the DSB-SC signal. So m of t is multiplied by the carrier cos of 2 pi fct, and this cos of 2 pi fct times m of t, it will get attenuated by some scaling factor. Let's say the scaling factor is k times, therefore you are receiving k times m of t cos of omega ct. Now what will be the demodulator input now? it will be k times m of t cos omega ct. So this is given to the demodulator. Okay, so in fact this is a band pass signal. Here the noise is getting added n of t and give it to the band pass filter. It is centered around the carrier frequency omega I. So in this point the n of t becomes ni of t, and the same signal will appear here also. So let me say this point is yi of t. Yi of t is equal to k times m of t times cos omega ct plus ni of t. Okay, yi of t is the notation for the signal which is present at the input of the demodulator. What is the demodulator? The demodulator contains a multiplier again followed by low pass filter, and this is the demodulated output. So in this point you have Si and Ni, and here you have S0 and N0. Okay, so what is your Yi now? Same calculation. Y suffix I of t is equal to k times m of t cos of omega ct. What is Ni of t? It is narrow band noise that will be represented in terms of in phase component and quadrature phase component. So nc of t cos omega ct plus n suffix s of t sin omega ct. Okay, now this whole thing is multiplied by the low pass filter, multiplied by the cos signal. Let us say the cos function is cos of omega ct. Okay, let's say you are multiplying 2 times cos omega ct. So k times m of t cos omega ct plus nc of t times cos omega ct plus ns of t sin omega ct. Before that you can do one small arrangement here. What you can do is you can combine the cos omega term separately, this guy and this guy. K times m of t plus nc of t, the whole thing is multiplied by cos omega ct plus ns of t sin omega ct, then you multiply by 2 times cos omega ct. Now cos and cos becomes cos square k times m of t plus nc of t multiplied by cos square omega ct plus ns of t sin omega ct times, you put 2 here, 2 times ns of t times cos of omega ct, and this cos term and sin term are orthogonals, so therefore this leads to 0, and this you can write as 1 plus cos 2 omega ct. Therefore k times m of t plus n of t multiplied by 1 plus there is 2, that 2 I forgot here, 2, so we put 2 here. This 2 is coming from here, cos 2 omega ct divided by 2, and this 2, that 2 will get cancelled. You multiply term by term, k times m of t plus n of t plus k times m of t plus n of t multiply by cos of 2 omega ct. Okay, and this one is, let's say, y1 of t. Let me call this point is y1 of t. Now this y1 of t is given to the low pass filter. So after low pass filtering I get y0 of t. So this guy is removed because it is band pass signal by the low pass filter. Therefore you obtain k times m of t plus n of t. Sorry, this is not n of t, n suffix c of t. I am sorry, I forgot to put here n suffix c of t, in phase component. So this is noise, and this one is your signal part. Okay, so output signal power is equal to k square times m square of t bar. And this one is this one is not given in the problem. In the problem, input power is given, which is 1 microwatt. Okay, so SI is equal to 1 microwatt. So what is the input signal power to the receiver? Sorry, what is the input signal to the receiver? Input signal is k times m of t times cos omega ct. This is what we are giving to the receiver. Look at the figure. Okay, so this is my yi. The yi, the input signal is, this is my input signal, and this input signal is given to the demodulator, and this block is demodulator, DSB-SC modulator. So what is the input signal power now? This power is going to be k square times m square of t by 2. So this one is given by 1 microwatt. So k square m square of t from this is 2 microwatts. Okay, and then you substitute back here. Your output signal power is this one. So from the input power, it becomes very messy. Let me write down properly. This is SI. My input signal is k times m of t cos omega ct. If I calculate power, this is my power, input power. And the input power is given in the problem, that is 1 microwatt. So you take this 2 to the right hand side, k square m square of t is equal to 2 microwatt. But this k square m square of t bar is nothing but your output signal power. Therefore, S naught is equal to 2 times 10 to the power of minus 6 watts. This is S naught. Okay, so output signal power is known now. The only thing to left is the output noise power. So what is output signal? If you look at the demodulator, output of the demodulator is NC of t. So what is the power of this guy? NC square of t, right? So this is nothing but same as your n square of t. And now this is the noise power in the narrow band noise with a bandwidth of 2B. Okay, so but I can't simply multiply n by 2 times 2B because it is not constant. The power spectral density is not flat. It is so therefore we have to do the integration. See, in the earlier case we said it is like this. If it is constant, then you can multiply. So this is 2B. So 2B times n by 2, here also 2B times n by 2, like that you can do. But here you cannot do like that, because the given power spectral density function Sn of f is equal to 1 divided by omega square plus a square. It is not constant. Okay, so therefore noise power n naught is equal to, it looks like this, like this, like this. This is Fc, and this point is Fc plus Fc minus B. This point is Fc plus B, and this point is minus Fc. This is minus Fc plus B, and this point is minus Fc minus B. So I need to integrate from this point to this point, and from this point to this point. Okay, therefore my output power n naught is equal to integral of minus Fc minus B to minus Fc plus B Sn of, maybe I can put omega, no problem, Sn of omega times d omega plus integral of Fc minus B, this limit, this guy, and then upper limit is Fc plus B for this curve, Sn of omega times d omega. Am I correct? No, I'm sorry. I'm very sorry. What did I do? My function will be like this. So you are integrating between this point. I am very, very sorry. This is my Sn of omega. So symmetric regions, you are integrating this region and this region. I'm very sorry about that. So this is, again, this area is the same as this area. It is even function because power spectrum is an even function. Therefore, let me put 2 times integral of fc minus b to fc plus b 1 by omega square plus a square times d omega. Okay, and now let me write down in terms of, because since I am using fc, then let me write down in terms of f. This all things let me write down in terms of f. Sn of f df, Sn of f df. So this also you can write in terms of 2 pi f the whole squared, and this one you write as f. So now fc is given. What is fc? 500 kilohertz, and b also given 4 kilohertz. Therefore 500 minus 4 is 496 kilohertz to 504 kilohertz. Okay, 3, then 1 by 2 pi f the whole square plus a square df. Now it's a straightforward, okay, definite integral, and you can do the integration. It is 1 by a square plus x square, that is tan inverse of x by a. So you just do this integration, and then finally your n naught, the left hand side is n naught, right? So therefore that n naught is going to be 8.25 times 10 to the power of minus 10 watts. You can work on it. S naught also just now we calculated, it is 2 times 10 to the power of minus 6 watts. So S naught by N naught is equal to it is 2 times 10 to the power of minus 6 divided by 8.25 10 to the power of minus 10. So this is going to be 2.42 times 10 to the power of 3, and this one is approximately equal to 23.8 dB. Okay, so that is the signal to noise ratio in dB. So we went through the simple calculations to get this idea. Okay, let me stop at this point. Thank you very much. That's it.